We're now going to have our last lesson in mechanics, and this is the second half of Chapter 7, which is on gravitation. Okay, we've already talked about the force due to gravity before, about how the fact that it attracts objects, causes objects to fall down. We've already investigated and proved that the acceleration due to gravity here on Earth is 9.81 meters per second squared. We're going to investigate that a little bit further because Isaac Newton was the one that also attempted to solve this problem, or tried to explain what gravity was. And in reality, he was actually trying to solve what he thought were two separate problems. The first, why is it that objects, if you drop them, all fall down? And separately, what he thought was separately, is why did the moon orbit around the Earth? Okay? And so what he actually found out was these two problems were actually linked and caused by the exact same force. Okay, and the first thing he was trying to do, or first thing he came up with, is the fact that he figured out that this force of gravity, this force of attraction between objects, was directly proportional to the two masses. And so if I increase my mass, I'm going to have a larger attraction to the Earth, because by increasing my mass, that's going to increase the overall force of gravity. Okay? Likewise, or if I just have this little pen here, it's not as attracted to the Earth as I am. The other thing he looked at was he actually looked at a guy by the name of Kepler. Okay? And there's a wonderful little story behind Kepler. I can explain it tomorrow in class, but just know that he did a lot of research on the position of the planets and where they were at all times. And by analysis of that, Isaac Newton figured out that the force due to gravity was inversely proportional to the square of the distance between two objects. And the way that he came up with that was that he was able to calculate out the acceleration of the moon going around the Earth. And he found out that that was approximately equal to 1/3600th of the acceleration due to gravity here on Earth. Okay, so that was the acceleration of the moon. That's what you centrifugal acceleration of the moon. And then also from Kepler's research and analysis, he was able to show that the distance between the Earth and the moon was approximately equal to 60 times the radius of the Earth. And so if you do 1/60 squared, you get 1/3600th. And so from these two things, and I'll circle this in green, from these two things, he was able to develop his law of gravitation, which states that the force due to gravity between two objects is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. Now, you'll notice that this is not an equation. This is a proportionality. And so if I double one of the masses, I'll double the force. If I double both masses, I'll quadruple the force. I should put a little g here because it's a force due to gravity. If I double the radius, then I'm going to quarter that force due to gravity. But we can't use it to do an equation yet. And that's because it doesn't have the same units. The units of my force due to gravity are newtons. It's a force. The units of this concoction are kilograms squared over meters squared. Okay, they're not the same thing. And so another guy had to come along, okay, by the name of Henry Cavendish in 1797. And he used what's called a torsion balance. And I'll explain that in more detail tomorrow in class. But he was able to determine a constant of proportionality. By doing some investigations, he was able to plot the force due to gravity versus the product of the masses over the square of the distance between them, and was able to show that that was a direct relationship. And so when he found the slope of this graph, the slope of this graph was equal to a constant. And that constant comes with a capital letter G. Let me clean that up so it doesn't look quite as ugly. A capital letter G. And it comes with, when he found the slope of this, he found that G, or the slope, was equal to 6.67 times 10 to the negative 11th Newton meters squared over kilograms squared. And so when he found this out, this became that constant in order to figure out, so we could now create a formula. And that formula becomes the force due to gravity is equal to big G times M1 times M2 all over R squared. And this became Newton's universal law of gravitation, which shows that the force of gravity, the gravity is an attractive force between all objects in the universe. And the size of that force is going to be dependent upon the product of the masses. So bigger objects have a larger amount of force between them. And it's also inversely proportional to the square of the distance between them. And so the further they get away, the force of gravity becomes less. Notice though, just a little tidbit here, at no point in time does this force due to gravity ever become zero. It may become very, very infinitesimally small, but there's always a force due to gravity, which means that you are attracted to the Earth, yes, mainly, but you're also attracted to the moon. You're also attracted to the sun. You're also attracted to Alpha Centauri, a star far, far away, roughly 3.2 light years or so. Okay? That force of gravity is always there. Now, we've already spoken about the acceleration of gravity. We know that the acceleration of gravity here on Earth, G, is 9.81 meters per second squared. But remember from Newton's second law of motion that acceleration is equal to F over m. And so I'm going to rewrite this. I'm going to put it in green. This becomes that my acceleration of gravity is found by taking the force due to gravity and dividing it by the mass of the object, or big G m over r squared. So if you take that force of gravity equation, big G m1 m2 over r squared, divided through by one of the m's. And so this m, I'll highlight it, this represents the mass of the object that's doing the attracting. Okay, so if I want to find the acceleration of gravity of the Earth, I'm going to use the mass of the Earth there. And then the distance away from the center of the Earth. If I want to find the acceleration of gravity of me, you know, what's the acceleration that people have towards me, I would use the mass of me and divide that by the distance you are away from me squared. Okay, and if you calculate this through, you're going to get 9.81 meters per second squared if you use the mass of the Earth and the radius of the Earth squared in our gravitational constant. So please notice that as you get further away, the acceleration of gravity will decrease. Okay, and we've already talked about that before, how the acceleration will change with your elevation. Now, we know that gravity is a field force. You don't have to have contact in order to have gravity. Nothing reaches up and pulls us down to the Earth. Okay, there's nothing up top pushing us back down to the Earth. It is a field force. Okay, and so what they did was they came up with the idea that if this is my Earth, and I'm going to use Earth as an example, if I look at it two-dimensionally, there's a gravitational field which is constantly pulling you towards that surface as such. And the size of the force is dependent upon, not dependent upon, is illustrated by how close the lines are together. And so the closer the lines are together, the stronger the force is on it. And so this is your gravitational field. It is not a contact force. It is a field force. Yep. And so we can now find that gravitational field. This is a different way of describing it. The gravitational field is defined as being the force per unit mass, which is how we found our acceleration due to gravity to begin with. And so this G, although it does have the exact same symbol as our acceleration due to gravity, this is known as our gravitational field strength. Okay? And its units are newtons per kilogram. Okay? Now, although because of how we set this up, I shouldn't say it, because of how we set this up, this gravitational field strength is always going to be equal to the acceleration of gravity. Please realize that's how we set it up. They are actually two different concepts. The acceleration of gravity is how much does the velocity of an object change every second. This is how much force per unit of mass an object exerts on another one. because of how we set it up. They are the exact same number, but they're technically two different concepts. Okay. So we'll talk about that a little more too. Okay. So again, we talked about this. As you get further away, the gravitational field strength goes down. Okay. And it's actually the interaction of these fields that causes this gravitational force, causes this attraction. Now, the last two things we're going to talk about in this chapter are weightlessness. There are actually two different types. The first is called apparent weightlessness. And this is actually, a better name for this is actually free fall. If you've ever been in like the power tower or the demon drop at Cedar Point, and you get the whoop as you fall down, they were actually technically weightless for that time. Little side story here, and I'm telling you not to do this because I've had at least one of my physics students kicked out of Cedar Point for this. But if you go to the top of the demon drop or whatever the name is, power tower, it's up there, and you were to place a coin and put it on your lap, okay, and then it dropped down, you would actually see that coin hover above you, above your lap where it lay there, okay? And so as you fall down, everything appears to be weightless. I'm going to show you a video where they have the vomit comet, where astronauts go train to be in microgravity, where basically a plane will go into free fall, it'll dive down. And when it does that, everything on the inside is falling at the exact same rate. And so apparent weightlessness is actually the lack of a normal force. Remember how we talked about how the normal force is actually how we perceive our weight. When you step on a scale, the scale reading is what the normal force pushing you back up in order to make sure you remain in equilibrium. Okay? If you get rid of that normal force, you appear or you feel, you get the sensation of being weightless, even though the force of gravity is still acting on you. This is opposed to, okay, oops, I'll give you another example. Sorry, before I go on to the real weightlessness. If you've ever seen pictures of the International Space Station, okay, or the space shuttle, live feeds from those, basically what happens is, if this is your Earth, and let's say this is your, whatever, your satellite or space station going around, that's a really bad example. But what happens is as this thing gets sucked down, we know there's a force of gravity pulling it down. It's pulling it down towards Earth, but as it's going, it actually has a velocity pulling it this way. So in reality, when it goes around, it actually falls around the Earth. And so it's continuously falling, but because its velocity is such, it falls around the Earth. It's another way how we know that the Earth is actually round, because you are falling around it. If the Earth is flat, you wouldn't fall around it. Okay? So this is how you get to be weightless when you're up in space. You are actually, you're still close enough to feel the effects of gravity, but because you are continuously in free fall, you will feel and appear to be weightless. The last thing we're talking about is actually real weightlessness. And again, as we said before, the force of gravity never goes to zero, but eventually, if you get so far away from a large object, if your R squared becomes really big, then your force of gravity gets really small. And if you've ever seen the movie Apollo 13, where they're going to the moon and they have the accident and everything else, they're floating around, they were actually really weightless because they were so far away from the Earth and the moon that they actually, the force of gravity were actually negligible on them. And so they actually appear to be weightless. Okay? So this is a great way to end. This is the end of mechanics. We now have a good idea, a better understanding of how and why objects move and are able to predict that movement and to analyze that movement. So tomorrow we'll work on this and then we'll start reviewing for our first major test. So everybody have a fantastic evening. See you later. Bye.